So in my last video, I asked you to calculate how many 5-inch pizzas would equal one 10-inch pizza. If you remembered your high school math, you pulled up pi r squared as the area of a circle and figured out the areas and realized it took 4 of the small pizzas to equal the large. For the 9-inch pizzas, the number of 5-inch pizzas is 3.24. Finally, for the 3-dimensional pizza balls, you likely used the equation for the volume of a sphere and realized that it took 8 of the small pizza balls to equal 1 of the large pizza balls. Just using the equations to calculate their areas or volumes works, but there's a faster, more generalizable way. But first, I promised you a story about pizza balls. A Kansas pizza shop owner discovered that DoorDash was paying him more for his pizzas than the people were actually paying the app. So he exploited the arbitrage to buy pizzas for himself, pocket the difference, and send pizzas to his friends and family at DoorDash's expense. Eventually, he realized he didn't even need to make real pizzas, but could just send out balls of dough, which was what he did. So pizza balls are real, you guys. Next, this viral tweet about an obnoxiously math-minded customer who seems to be buying pizzas at a pizza shop for ants, a pizza shop that has sufficient dough but inexplicably can't make a larger-sized pizza. A number of other Twitter users noted that the story had been posted many times before by others, and in the end, @RetiredRoy admitted that the pizza shop incident never happened. Most good stories aren't true. Now, an easier way to solve the pizza questions above is to not even calculate the areas, but to divide one algebraic expression by another before you even punch them into a calculator. Easier still, just notice the scaling of the quantities in mind. We take it for granted that for a scale model of something, all the lengths just become larger by that same amount, called the scale factor. Let's call this C. But the surprise that comes with this is that many quantities aren't linear in length. Area, for example, scales with the square of the length. Making a model 3 times larger means its areas become 3 squared, or 9 times larger. This is why a square meter is 10,000 square centimeters, and not 100. Volume, meanwhile, scales with the cube of the length. Making the volume C times larger makes the volume C cubed times larger. Doubling every side makes the volume 8 times larger. But so what, you say? So you can find out trivia about high school geometry shapes. What application does this have in the world besides making up stories about outsmarting your pizza waiter for dubious internet fame? It turns out, area and volume also tell you things like how much steering an airplane control surface has, how heavy parts of a building are, and how easy it is to dissipate heat. This general principle is called the square-cube law and has many applications. As you get to larger versions of the same shape, the surface area never keeps up with the growth in volume, so your surface area to volume ratio shrinks. So larger objects retain their heat better. The Mall of America in Minnesota, the country's largest mall, has to run the AC year-round, even in Minnesota, because it never dissipates all the heat produced through the moving people and lighting. Rocket engines have the same problem when they get very large because they can't dissipate heat fast enough. The same is true for diffusing particles as well as heat. Now, because density is an intrinsic quantity, volume is proportional to mass, inertia, and weight, so scale model large versions of things are harder to support, steer, and control than their smaller counterparts, though they do have more stability. Wikipedia user Icarus snapped a photo that illustrates this principle beautifully when they captured a smaller Boeing 737 in front of an Airbus A380. The fuselage is maybe twice bigger all around, but the effectiveness of the control surfaces and wings, which scale with the area, become nearly 3 times as large to create 8 times the area to make up for the 8 times as much inertia of the larger plane. The square-cube law is also the reason why hailstones are potentially fatal, while raindrops are not. A dollhouse can support itself from its own material strength. Its walls can be load-bearing. A full-size building, however, requires special bracing with high compressive strength materials to form a supporting skeleton. And speaking of skeletons, the square-cube law means that the bones of elephants need to be that much larger than would scale from smaller animals because, again, weight scales with the volume, even while strength scales with the area. Also, why King Kong couldn't take a step without his bones breaking. This is also the reason why none of those human wing flapping flight designs ever worked. The lift needed is proportional to the weight, which scales with volume, but the lift you actually get only scales with the area. And so you can see how a relatively simple question about pizza sizes could give you a greater appreciation of the world around you and why things are the sizes that they are. So thanks for watching. Remember to stay coffee snobby.